Hello and welcome. My name is Franz Polster. This is the first of two videos on numerical methods for the calculation of exponential approximations. It is a follow-up to my video on the theory of exponential approximation. Familiarity with that video is assumed. In particular, the terminology introduced there, as well as the statements, corollaries, etc. of the theory, will be used without further explanation. Three algorithms will be presented which calculate simple exponential approximations for continuous functions. These are the algorithms of Meinardus, Willers, and Rice. These are direct, non-iterative algorithms. They try to solve an interpolation problem in order to calculate the coefficients of an exponential sum, which is to approximate a given function f. In general, they do not deliver best approximations. Numerical methods for the calculation of best approximations are the subject of the video Iterative Algorithms. Let us start with the algorithm of Meinardus. The approach of Meinardus is to find an exponential sum e of v sub n 0 such that e is equal to f at 2n equidistant points xn of interval I. This can be thought of as an interpolation problem with 2n function values. An example to illustrate this approach. Function f is the square root of x, n is equal to 2, and these are the four equidistant points x0 through x3 in interval I. Application of the algorithm of Meinardus results in these coefficients ai and ti. At points x0 through x3, the exponential sum with these coefficients has the values of function f. In other words, the equidistant points are zeros of the other function e, shown here in this graph. Clearly, this is not yet an alternate of length 5. Thus, this exponential sum is not the best approximation, but it is close to an alternate, and this exponential sum may serve as a starting value for iterative methods for the calculation of a best approximation. In any case, this is an upper bound for the norm of the error function of a best approximation. So, the problem consists in calculating 2n coefficients ai which satisfy the system of equations 1 with this set of equidistant points. Meinardus tackles this problem as follows. With these definitions of capital HA and capital EJ and FJ, we can rewrite system 1 and arrive at the equivalent system of nonlinear equations 2 with the two unknowns capital HA and capital EJ. This system is transformed into this system of equations with the two n unknowns pi and qi, where the qi in equations 3 and 4 are the coefficients of polynomial q, and the pi's in equation 3 and 4 are the coefficients of this polynomial. This derivation involves non-trivial reasoning including application of a method by Srinivasa Ramanujan. You'll find the details in reference T2. Notice the n coefficients qi are the only unknowns in equation 5. That is, equations 5 form a system of linear equations. So we can hope to solve the original interpolation problem 1 following these steps. Solve the system of linear equations 5, which gives us the coefficients qi of polynomial q. Then find the zeros ci of q. They will give us the coefficients ti due to these equations. Equations 4 with the qi plugged in form a system of linear equations, the solution of which are the coefficients pi. Finally, with these coefficients pi, the coefficients ai can be calculated according to a theorem by Meinardus, or alternatively, with the values of the coefficients ti given, the original interpolation problem 1 forms a system of linear equations, the solution of which are the coefficients ai. This is the rationale for the following algorithm. First, solve the system of linear equations 5. The existence of a solution is not guaranteed. If there is no solution, the algorithm terminates with failure. If a solution exists, determine the zeros of polynomial q. If q has n pairwise different real zero ci greater than 0, this formula gives us the coefficients ti. Otherwise, the algorithm terminates with failure. Solve equations 4 with the values for qi plugged in. This yields the coefficients pi. With these coefficients pi and the zeros zi, calculate the capital A case using this formula by Meinardus, which finally gives us the coefficients ai. Obviously, we cannot be sure that this algorithm always solves the interpolation problem 1. However, Meinardus has shown that if a solution exists, then the algorithm will yield a solution, which then is even the unique solution. The choice of the equidistant points is crucial. If the goal is to come up with a good approximation, meaning the error function is close to an alternate, then in general points x0 and x2n-1 should not be border points of interval I. Remember, this was the case in the example above. In other words, finding the right set of equidistant points is a trial and error process. These are experiments that have been performed with the algorithm of Meinardus. This column shows the number of different sets of equidistant points employed. The algorithm produced exponential sums for all these functions f. However, this function is a good example of how laborious finding a useful set of equidistant points may become. The algorithm was successful for only 3 out of 11 sets of equidistant points. The other 8 resulted in failure due to complex zeros Ci. Check reference C1 for detailed information on these applications of the algorithm of Meinardus. Next is the algorithm of Willers. The idea of Willers is quite similar to that of Meinardus. Willers tries to construct an exponential sum e of v sub n0 such that e is equal to f at 2n or more equidistant points of interval I. Again, this can be thought of as an interpolation problem, but here with the option of more than 2n function values. In order to calculate the coefficients ai, ti, we have to solve this system of nonlinear equations 6 with m equal to or greater than 2n. Similar to the approach of Meinardus, with these definitions of capital AI, capital EI, and FI, equation 6 are transformed into the equivalent system of nonlinear equations 7 here, with the 2n unknowns capital AJ and capital EJ. From this system can be derived system 8 of m minus n linear equations with n unknowns qi, which are the coefficients of the polynomial with n zeros capital EJ. This derivation involves non-trivial reasoning. You find the details in reference T2. So we can hope to solve the original interpolation problem 6 following these steps here. First, solve the system of linear equations 8, which gives us the coefficients qi of polynomial q. Then find the zeros capital EJ of q. They give us the coefficients ti due to these equations. Then equation 7 with the capital EJ's plugged in form a system of linear equations, the solution of which are the capital AI. The AI in turn will give us the coefficients AI due to this equation. This suggests the following algorithm. First, solve the system of linear equations 8, which, depending on the number m of equidistant points, may consist of more than 2n equations. If m is equal to 2n, the qi are the solution of a system of linear equations. If m is greater than 2n, the qi are calculated using the method of least squares. The existence of a solution is not guaranteed. If there is no solution, the algorithm terminates with failure. If a solution exists, determine the zeros of polynomial q. If q has n real pairwise different zeros greater than 0, this formula gives us the wanted coefficients ti. Otherwise, the algorithm terminates with failure. Equations 7 with the zeros plugged in form a system of linear equations. The solution of this system are the capital AI's, which finally gives us the wanted coefficients AI. With 2n equidistant points, the Willers algorithm is basically identical with the algorithm of Meinardus. Obviously, we cannot be sure that this algorithm always solves the interpolation problem 6. Here too, the choice of the equidistant points is crucial, and finding an appropriate set of equidistant points is a trial and error process. Numerical experiments indicate that more equidistant points do not necessarily result in better approximations. For instance, the algorithm has been applied to function square root of x, employing 3 sets of 10, 22, and 32 equidistant points without producing better approximations. The algorithm failed for this function on the same 3 sets of equidistant points. No exponential sum could be computed. For all of them, the zeros of polynomial q are complex, not real. Remember, also the algorithm of Meinardus produced quite a few failures when applied to this function. This concludes the presentation of the algorithm of Willers's. Next is the algorithm of Rice. Rice tries to find an exponential sum e of v sub n0 such that at 2n plus 1 equidistant points of interval I, the error function f minus e has a non-zero value r, the sign of which is alternating at these points. If the error function is close to an alternate of length 2n plus 1, you can hope that E is a sufficiently good approximation of f. So this can be thought of as an interpolation problem with 2n plus 1 values of a error function f minus e. As an example, to illustrate this approach, as for the algorithm of Meinardus, function f is the square root of x and n is 2. These are the 5 equidistant points x1 through x5, and the application of the algorithm of Rice results in these coefficients ai and ti. At points x1 through x5, the absolute value of the error function is r. In the graph, here, 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 and the fourth. Clearly, this is not an alternate of length 5. Thus, this exponential sum is not the best approximation, but it is close to an alternate, and this exponential sum may serve as a starting value for iterative methods for the calculation of a best approximation. In any case, this here is an upper bound for the norm of the error function of a best approximation. Note, it is just slightly greater than that of the Meinardus example. So, the problem consists in calculating 2n coefficients ai, ti, which satisfy the system of equations 9 with the 2n plus 1 equidistant points xj. Addition of successive equations of this system removes the unknown r and yields the system 10 of 2n equations. From this system can be derived polynomial p of x, which is the determinant of this matrix, the zeros of which are the e to the TIH. Again, this involves non-trivial reasoning. You find the details in reference T2. So we can hope to solve the original interpolation problem 9 following these steps. Find the zero Ci of polynomial p. They give us the Ti due to this equation. Equations 9 as well as 10 with the TI plugged in form systems of linear equations, respectively, with the unknowns AI. Solution of one of these systems yields the coefficients AI. This suggests the following algorithm. Determine the zeros of polynomial p. If p has n real pairwise different zeros greater than 0, this formula gives us the wanted coefficients Ti. Otherwise, the algorithm terminates with failure. Solve the system of linear equations 10 with the coefficients Ti plugged in. The solution vector consists of the wanted coefficients Ai. Obviously, we cannot be sure that this algorithm always solved the interpolation problem 9. Due to the calculation of determinants, this algorithm may be susceptible to rounding errors. Again, the choice of the 2n+1 equidistant points is crucial. Finding an appropriate point set is a trial and error process. The algorithm produced exponential sums for both functions shown here. However, again, this function is a good example of how laborious finding a suitable set of equidistant points may become. The algorithm of Rice was successful for only 1 out of 5 sets of equidistant points. For 4 point sets, the zeros of polynomial p are complex, not real. Check reference T2 for details. These are the references used in this video. They are available in the web at this address. Thank you for your interest. You are welcome to move on to the video on iterative algorithms which compute best approximations. Goodbye and see you there.